Hello, Dynamics World! This is Weather Girl Victoria reporting to you from Morse Library at the University of Delaware. Today, we have a slight drizzle of dynamics problems for you. For our problem, the groove drums in the two systems are shown are identical, as you can see in A and B. In each case, A and B, the system is at rest at time t equals 0. We must determine the angular velocity of the groove drums at the time t equals 4 seconds for both cases. But we must neglect any, velocity that might be coming from the rain, of course, Calculate the tension in the cable for case B, but only for case B. Note that the radius gyration of the drum is 225 millimeters, but neglect the friction at the pivot point O, which is here and here in both cases. And now we'll come at you with the first part of this dynamics problem. Stay tuned with these slight interruptions. Our initial conditions before the terrible rain that comes. So here we have our two groove drums. This is A and this is B. So for both drums, they have the exact same initial conditions with a initial radius, or the inner radius being 0.215 meters and the outer radius being 0.325 meters. And both groove drums have a radius of gyration of 0.225 meters. And both the masses of both drums is 14 kilograms. What differs, groove drum A has a force acting on it, while groove drum B has a mass hanging down on it, which results in a tension with this groove drum. Thank you. And now, we're off to solve the first part of the problem. Hopefully the rain doesn't become too much. Hello, there's been a downpour of equations for our dynamics problem. Oh, the equations are pulling me away. And now we'll be going on to our first part of our problem. Here we have our free body diagrams, and this is the groove drum at the beginning when time equals 0 and it is at rest. And then here's the groove drum where the moments are affecting the angular velocity. And then we have the final groove when at time equals 4. This is how the groove drum is appearing with our free body diagram. In this problem, we have to use the impulse and momentum equation, which is shown here. And so initially there is no angular velocity, so that means that this part of the equation goes to 0. And the impulse does not affect the final angular velocity. But the moments about the groove with the groove drum, they do affect the final angular velocity. So we do take into account from 0 to 4 seconds with the force of around the origin times the radius of the small part of the groove drum, which results in the impulse times the angular velocity. And we find the impulse from mass times k squared, and k is our radius of gyration as seen here. And in conclusion, we find that our angular velocity for our groove drum A is 119.035 radians per second. Thank you. Now we are going off to our next part of our problem, which our meteorologist, Kirsten Leahy, will be telling you about. And here she comes.
Hello, I'm Kirsten Leahy, and I'm reporting live with the second part of our dynamics problem. As you can see here, we are still using the impulse momentum theorem to solve this part of the problem, but it looks like our rainstorm has brought us a new equation for our IG. Our IG now equals mk squared plus mri squared. So our first part is still at rest, so the groove drum is still at rest at time t equals 0, so our omega 1 is still 0, making this part of our impulse momentum theorem 0. And then for the moment part, we have the sum of mg, which is our weight, which is 98.1 newtons, times our inner radius, which is 0.215 meters, and that is all over the integral from 0 to 4 seconds. And then for our last part of the impulse momentum theorem, we have our m of the whole entire groove drum, which is 14 kilograms, and that times our radius of gyration, which is 0.225 meters squared, and that is added with 10 kilograms, which is our weight of our little thing right there. I don't know what that is, but it's there. And then that is times multiplied by our inner radius, which is 0.215 meters squared. And then all that is multiplied by our omega 2, which is what we want to solve for this. After solving our integral and dividing, which ends up being 84.366, and you divide that all by this right here, which ends up being 1.171, our omega 2 value is 72.046 radians per second. Now, here is Ari Klatz with our last part of our dynamics problem.
We're back with the final part of our dynamics problem. This is Ari speaking. Here, take a look. Things are getting really tense in here. So, as you can see, we want to find the tension in the cable holding the weight. For that, we have to convert the angular velocity of the drum to a linear velocity for the weight. We just use basic kinematics for that. We can use the linear momentum and impulse theorem that by adding the forces in the y direction will get us the tension. Simply like this, we found that the tension of the cable was 136.83 Newton. Thank you very much, and we do that.
That's all for today, folks.
Thanks for tuning in.
See you next week when we report about the deadly hit of final exams.